Question 6, a tricky question this. So you've got cyclohexene, so it's got 6 carbons, it's got 2 hydrogens on every carbon, except on this one we've got a double bond, so we've just got a double bond here. And if we add hydrogen across the double bond, it gives out its exothermic by 120 kilojoules per mole. So if we had 3 alternate double bonds, like in Kekulé, we expect it to be minus 360. But it's not. It's less than that. So it's not as exothermic. So this means that when we add 3 lots of hydrogen, 3 moles of hydrogen, actually it's not as exothermic. Something that's not exothermic is stable. Something that's less exothermic than you think is stable. So benzene is more stable. Anyway, it asks us to explain the bonding and the shape of the benzene molecule. So what you've got is, you've got hydrogens on each corner, 1 hydrogen on each corner, and each carbon is bonded with a covalent bond to 2 other carbons. The 4th bond is this ring, and now we need to explain this ring. So each carbon has 3 covalent bonds to a hydrogen and to 2 other carbons, we've mentioned that, and then the 4th electron, which we call a spare electron, overlaps to form the ring. That's the best way of saying that the double single bond doesn't really exist, and that there's delocalization, there's some movement of electrons, so we don't get doubles and singles, we get movement of electrons. So the spare electron, the 4th electron that should be in a bond, overlaps. Overlaps means it's shared between each of the 6 carbons. Each of the carbons has a spare electron, and it's shared around, and it moves, and it's delocalized. So the spare electrons on each of the carbon, the 4th electron overlaps between the carbons, and the electrons are delocalized. Just something to remember. What else do we need to know for 6 marks? It's flat, it's planar with 6 carbons in a ring, and all of the carbon-to-carbon bonds are equal length. That's how we know that they're not alternate double and singles, that they're all equal, and that's sort of explained away by this 4th electron overlapping between each carbon and being delocalized and moving around the ring. So stability. So benzene is more stable than you'd expect. So expected enthalpy of hydrogenation is, if it had 3 double bonds in there, 3 doubles and 3 singles, it would be minus 360. So adding 1 hydrogen across hydrogen molecule across double bond releases minus 120. So if it were 3 double bonds and 3 singles, 3 hydrogens should release minus 360, but there's a difference of 152. So if you take the 208 away from the minus 360, it's 152 kilojoules away from the value that we'd expect. That shows that benzene's more stable. It gives out less energy when it reacts. That means it's more stable. A tough question. The enthalpy of hydrogenation of cyclohex at 1,3-diene, so that will be with a double bond and then a single bond and a double bond, so a double, single, double, is not exactly double that of cyclohexene. So cyclohexene, when we add a hydrogen across the double bond, it's minus 120. There's another chemical called 1,3-diene, 2 double bonds, one at carbon number 1 and the next one at carbon number 3, so it would be a double, single, double, and it's not minus 240. It's not double. It's not quite double. It's not exactly double. Suggest a value. So you could have anything between above 120, above minus 120, and in between minus 120 and double is minus 240. You can have anything in between that because it says it's not exactly double. So you can have anything from minus 239, which is sort of double 120. So It's not quite double, so 120 doubled would be 240. It says it's not exactly double, so it's somewhere in the middle, somewhere between any number in between minus 120 and minus 240, which would be double. Suggest a value for the enthalpy of hydrogenation of cyclohexene and justify its value. We've done that. So double bonds are separated by one single bond, but there may be some delocalization. So that explains why it's more stable than you'd expect. Double bonds separated by a single bond, but there may be some movement of electrons between the two bonds. So it might not just be double, single, double. Sometimes there's movement of electrons even between two double bonds separated by a single. Difficult question.